Okay. So, did you guys get a chance to look at the rest of the material from where we finished last time? So we started talking about the covariance matrix, and we discussed some of the properties, and then I asked you guys to take a look at the proof of this result. So anyone got a chance to go over that? Do you hear me? Okay, so let's see in the chat. Okay, okay, so I think I see us 3 yeses, I think, in response. So you guys, Diana, Kilara, and Sehong, you all looked at it. So one of you wants to tell us about what this result is about and maybe a little bit about the proof. So should I call on one of you, or you want to volunteer? No, it's okay. Sehong, do you want to say something, or you can also, like, you could say I'm going to answer myself, or you could call on one of your other friends, like students. We're going to play this game.
I understand a little, but
okay.
Yeah.
Okay, go ahead.
What am I supposed to?
So what is this lemma tree about?
Oh yeah, so I can factor out the non-random variable A and A transpose Y versus random.
Y is random, yes. A is non-random. So what this is trying to achieve? So what this lemma is trying to? So it's trying to compute. So this gives you a way to compute the covariance of a new vector, right? So if you have the covariance of Y, this tells you how to compute the covariance of A times Y, which is a new vector, right?
Right.
Right.
Allows to compute the variance of linear combination. Random variables.
Right, that's a special case, but this is, so A times Y is in general a vector. So it has a covariance matrix, and this allows you to compute the entire covariance matrix. Computing the variance of the linear combinations of the elements of Y is a special case of this. Okay, so how about the proof? Do you remember how you prove this?
Yeah, so let
X be what?
AY.
Okay.
The X tilde.
Yeah.
For X minus expectations of X.
Okay.
Which is the convert X equals to AY.
X equal A. So what was that again? Sorry.
So X equal AY. So the X tilde. Okay.
Yeah, I've written these things that you mentioned. So then the next step, what is the next step?
X tilde is going to be AY minus expectation of XY, AY.
Okay.
And then AY, the inside of an expectation A is factored out A, yeah.
Okay.
And the entire things, the A times y minus expectations y.
Okay.
But it's the y minus expectation y is the y tilde.
Okay. So this step, what property or why this is true? Expectation of ay is a times expectation of y.
The lemma one.
Okay, like linearity expectation. Okay. So then the next step. So we have x tilde is a times y tilde. So how do you compute the covariance of?
So covariance x is expectation x tilde.
Right, x tilde
and
transpose. Okay.
And go with x expectation a y tilde.
Okay.
A y tilde transpose.
A y tilde transpose. Okay. Then?
And combining together the a y tilde transpose a transpose.
Sorry, so I didn't get it. So how do you simplify this?
Yeah, expectation a y tilde.
Yes.
And y tilde transpose times
Okay.
a transpose.
So why is this?
Because it's a is non-random by the lemma number.
No, this step is true even if a is random. So what property did we use here? Anyone else?
The BAC was the lemma 2.
We haven't used lemma 2 yet. This is a good, but why this is the case? Anyone? Well, I'm gonna come back to the second one, but let's say one of you other guys that, so Gilar, do you know how this, or Diana? Maybe Ethan? How do we write this step? Any? My roommate's taking quiz. Okay. Can you do it in the chat? So what property are we using here? So let's say if I have two matrices, product of two matrices, how do I transpose?
Oh, can you transpose each one? Like B transpose, C transpose?
Okay, is this correct?
No, I'm sorry, the other way.
Okay, great. That's the idea. So when you transpose a product, you reverse the order and transpose individually and then reverse the order. That's also here, right? So that's the important thing. Otherwise, the dimensions would not match. So let's say if this was n by 1, this was 1 by n, then this would be 1 by, sorry, this would be n by 1. This would be 1 by n. So the dimensions are fine. Otherwise, you would get 1 by n. So the B transpose, C transpose would have a different dimension. It would be n by 1. 1 by n. This would be 1 by n. N by 1, so the result would be one-dimensional, whereas this side is n-dimensional. So this is the correct one. And so we're using that. So transpose of this is individually, you transpose each term individually, and then you flip the order. Oh, okay, so Diana also pointed this out. Okay, yeah, that's good. So that's this, and then what's the next step? Maybe Sehun want to continue?
A
Yes.
expectation y tilde,
Yes.
the y tilde transpose, and
Okay.
A transpose.
So what is
The-
this one? This step.
Expectation y tilde y times y tilde is covariance of y
Right, but what? How do we get
by lemma
the step? Okay, this is lemma 2, and this is covariance of y. So we have shown the result. Okay. Okay, good. So now let me do. So suppose I have a vector x, which is x1, x2, x3, and I'm gonna tell you that the covariance of x is 1, let's say 0, 0, 1, and then 1/2, and then 1/4, 1/4, 1/4, 1/4. Whether this is a valid covariance matrix, you have to verify. I'm going to talk about that shortly. But let's hope that this is a valid covariance matrix. So covariance matrices have properties, certain properties that you need to verify. Let's suppose this is, assume that this is a valid covariance matrix. So now I'm going to ask you to compute the covariance, the variance of x1 plus x2 plus x3. Can you use that result that we discussed to compute something like this? Or is it not relevant? Maybe think a little bit about this. So this is a univariate random variable, and I want to compute the variance. How can we compute the variance? Just think a little bit about it, and I'll come back and chat about it. How do we do this? Anyone?
You could to represent x1 plus x2 plus x3, you could show the matrix multiplication as the vector 1, 1, 1 times the vector y1, y2, y3, and then to find the variance, you would just do the vector 1, 1, 1 times the covariance matrix of X, and then times the vector 1, 1, 1 transpose.
Okay, great. So the only thing that we have to like change is that this is X, let's say, not Y, but let's call this A, right? I'm going to call this A transpose, for example, right? So if I call this A transpose, what can we, can you restate what you said in terms of these notations?
Yeah, sorry. A transpose times covariance of X, and then, oh, sorry, A times covariance of
No,
X
that's correct.
times. Oh, okay.
That's good enough.
Okay.
Yeah. So that's A, right? Whatever goes here would be, so H, this is correct. And then
times
what's the
A.
Right. So that's the transpose. This is like A transpose transpose. Yeah, we could have called this A, but usually we work with column vectors, so it makes sense to call it A transpose. It doesn't matter. But if you call this A transpose, then the transpose of it would be just A. So then, okay, as you pointed out, this would be just 1, 1, 1, 1, 0, 1 fourth, 0, 1, 1 fourth, 1 fourth, 1 half. And then so you multiply it out and then you get your result. So let me ask you a question. Why, so this is about the covariance matrices, and here I'm asking for the variance. So why did you conclude that we can use that result? Or how did you conclude that?
Is it because like technically x1 plus x2 plus x3 is just like one random variable? So like,
Yeah.
so like the variance of one random variable is the covariance of like the random variable and the random variable, like just twice, kind of.
Yes. Okay. So yeah, great. So this is so variance. So if I call this a random variable z, variance of z is covariance of z and z. But here I'm using the covariance a little bit different. I'm using it differently. It's so I mean, if you want to do it, you could write it as covariance of ay. So the notation is a little bit confusing, but here what I'm saying is when I write it as a univariate function, not univariate, but with a single argument, then it means a covariance matrix. So when we write it with two arguments, it's I could do it for vectors, but usually I write it for, let's say if I write it as covariance, and these are scalar variables, then it's just the covariance of those scalar variables. And this is true. What we can say is that this is, in my notation, this is going to be equal to the covariance matrix of Z. So if when I write it like this is the covariance matrix. The notation is a little bit confusing, but because this is a 1-by-1 matrix, it has a covariance matrix, and the covariance matrix is just has one entry. This is like equal to the variance, if you want. So covariance matrix of Z is just a single matrix. So a matrix with a single entry, which is just the variance. And something like this is just it's just written as equal. So a matrix with one element is just a scalar. And so I can use the same formula. Yeah. So
this was the special case, the linear combination of random variables.
Yes, exactly. So you can compute the variance of a linear combination of random variables by noting that that linear combination can be written as A transpose X. And this is a 1-by-1 matrix. So it has a covariance matrix, which turns out to be its variance. and then you'd use A transpose cov x A, and then you go about your calculation.
So the final result is going to be scalar.
Yes,
So
yeah.
one single the vector. Yeah, okay.
Yes, the dimension of the result should be the same as what you expect. So if you started with covariance of a 1-by-1 variable, covariance matrix of a 1-by-1 variable should be 1-by-1, and the result would be a scalar. So, and then this is true here. So it would be a 1-by-3, 3-by-3, 3-by-1. So the result is 1-by-1. Yeah, this is the confusing notation. So some people actually use the notation variance here, which might be better. So I should probably change this. So some people write it as variance. And by variance, they mean the covariance matrix. And then reserve the notation covariance for the two argument operator. So you never write covariance. Maybe I should write it that way. Yeah, I forgot what your book does, but that's less confusing. So you can actually, in fact, you could, we can define a cross-covariance matrix. Cross-covariance matrix as the covariance of two vectors, let's say x and y, as expectation of, and write it as x minus expectation of x, and then times y minus expectation of y transpose. And so this is a more general operator. And so the covariance matrix that we defined was in fact cov x was cov xx. And this would be the general form. And then you could show let me do it here. No, this was not good. Sorry, let's try. Take this, move it here. Then you can show, for example, that covariance, cross covariance of A times by is A cov x and y B transpose by the same arguments. And so this would be a generalization of the lemma that we had. So does this make sense, people? Say a slide. Makes sense?
Yeah, it makes sense.
Okay, good. Anyone else has a question about this? No. Okay, so suppose, so back to the example above. How do we compute the covariance of, let's say, a subvector x1, x3? This just looks at the subvector. Maybe think a little bit about this.
Is a 2-by-2 matrix, the variance x1.
Okay, variance x1.
And covariance x1 and x3.
Okay.
And the symmetric, the covariance x3, x11 or whatever, and variance x3.
Yes, this is better, but they're equal, yeah. And then variance x3. So how did you get this? So in this case, this would be 1.
One and row.
Sorry?
Yeah. The
Yeah.
general.
Yeah, so it would be these entries. So it would be the corresponding submatrix of the covariance matrix on the indices. So you're choosing index 1 and 3. So you choose the submatrix on indices 1 and 3 for both the rows and columns. Okay, and so that's how you can read it. So I'm assuming that the way that you came up with this is using the definition of the covariance matrix, right? Was that the idea? So how did you come up with this? Anyone else?
Since it's like two random variables, you just use like the formula pretty much, or like you just follow how it's usually supposed to be arranged.
Yeah, so you could say by definition. So definition of the covariance matrix tells you what each entry should be. And so the entries would be like the first entry would be the covariance of the variance of the first element, and the second entry, 1, 2 entry would be the covariance of the first and the second element, which in this case is x1, x3, and so on. So this is, let's say, by definition, if you want. So now the question is that can I use this lemma to compute the covariance of such submatrix or subvector? So can we use lemma 3, let's say, instead? Which is to say, can I write this as A times X? As a matrix, like 2 by 3 times x1, x2, x3. And I can call this A and use that result.
I think you can, yeah.
Okay, what would that matrix be?
It'd be 1, 0, 0 on the first row, then
Yes.
0, 0, 0 on the second row. Oh wait, sorry, 0, 0, 1.
Okay, good. Yeah, so if you do this, the first row would select the first element, and then the second row would select the third element. And then you can write down the covariance of x1, x3 is just this A, 1, 0, 0, 0, 0, 1, covariance of x, and then times A transpose, which is 1, 0, 0, 0, 0, 1. And then you multiply out, and you would get this. So this operation would choose that particular submatrix. So choosing a subvector of a vector is a linear operation. So you can write it as, by linear, we mean exactly that it can be written as a matrix times that vector. Okay, so taking a subvector is a linear operation. Okay, so so what else? If you understand this cross-covariance idea, so what would be, for example, the cross-covariance? Let me do a little bit more. bit more interesting example, or just let's say, that's fine. So let's do covariance of x1 and x2, x3. This is the cross covariance between these two vectors. One is 1 by 1, the other is 2 by 1. You can take the cross covariance between any two vectors. So this should be a 1 by 2 object. The dimension would be the same as dimension of the first one times the dimension of the second vector. So based on the setup that we had, what is the cross covariance of x1 and x2, x3? Anyone? So based on this definition, can you guess at least what it would? So it's a 1 by 2 matrix. What would be the entries? No one can guess. So this is just going to be covariance of x1, x2, and then covariance of x1, x3. So if you go back to the definition above, it's just going to be this. So can I write it as covariance of, let's say, ax and bx? So can I write this as x1 as ax and the other one as bx? So the other one you already have some sort of an idea. So this is like 0, 1, 0, 0, 0, 1, just like the one that we did before, times x1, x2, x3. This one would be what? Anyone? See, Ethan.
Is it
Any-
1 0 0
Okay, 1,
0 0
0,
times
0,
x1 x2?
right. Great, okay. And then if you believe that formula, this is saying I can compute this exact thing by just doing like A times the covariance of X and X, and then times B transpose, which is going to be 0, 1, 0, 0, 0, 1. So if you do that, you should be able to get, so this turns out covariance 1. So the cross covariance here between 1 and 2, 3 would be, you go to the first row and then look at this. This is that cross covariance. And so you should end up getting, if you haven't done anything wrong, you should get this, and this should give you the same thing. So these are the easiest applications of these ideas where you just work with submatrices. So this is the cross covariance of x1 and x2 and x3. The cross covariance is not symmetric, so cross covariance, so covariance of x and y, and the covariance of y, x, these would be transpose of each other. Whereas for the usual covariance matrix, the things would be symmetric. So it's a little bit tricky, but so this addition of this generalization, I usually don't discuss, but it's a natural generalization that we can work with. Okay, questions, comments?
I have a question. For
Sure.
AX, like, what is it? Like, where'd you get the 100 times x1, x2, x3? Like, what's AX referring to?
I was talking about this. I'm trying to write this in terms of linear,
Oh, okay.
linear, right? So
Okay,
I can
yeah,
write
I get it.
x1 as this, right? Okay, good. Other questions? So let me ask you a question. So if you didn't know this lemma, let's say in a previous course, could you still compute this variance of x1 plus x2 plus x3? Do you know any other way of computing this?
Isn't there like some sort of formula?
There's always
Where
some
it's
sort
like,
of formula. Okay.
yeah,
But
it's like, I'm not exactly like, I don't exactly remember it, but it's like variance of, like, for example, like A plus variance of B minus covariance, or minus like 2 covariance of like AB, something like that.
great. Okay, so let's do it for two variables. Another approach. So what is the general formula for the variance of x1 plus x2?
Covariance
Covariance.
x1 plus x2, comma x1 plus x2.
Okay, good. That's true. So this is using the covariance operator. So the variance of the variable is the covariance of that variable itself. Okay.
And it's gonna be variance x1 minus 2 covariance x1, x2 plus variance x2.
Is this correct? How do you guys think about this?
It's a plus, right?
Okay, plus. So how did you come up with this?
Is that
Is just for memory, or is the procedure for getting this?
by your the previous recording?
But sorry?
By the previous your recording video.
Oh, really? Okay. But
Yeah.
so what did I say?
But,
How do you get this from the previous recording? Is there a rule to get this?
The bilinearity rule.
Okay, bilinearity.
Covariance.
Great. Okay, so bilinearity. So what is bilinearity? So the covariance operator is bilinear. Let's say the two argument, the one with the two argument. This operator is bilinear. So what does it mean? Anyone else got that far? I'm glad that you got this.
Is it related to the symmetry?
The symmetry is another property. So bilinearity is a different property. Something could be bilinear but not symmetric. So symmetry refers to cov x, y. So this is symmetry being equal to cov y x, which is for the scalar case. For the vector case,
okay.
you put a transpose. But what is bilinearity?
honestly, I was no time to.
Sorry?
I didn't have much time to review it. But,
Okay, so it's something like this. If I have a linear combination of two random variables, alpha and beta are constants, x and y are random variables. If I want to compute the covariance with this, it's linear in the first argument, so I can expand it like I would do with a linear operator. So it just expands like this. So it's linear in the first argument and linear, so linear in first argument and linear in the second argument. So cov, let's say x and alpha y plus beta z, that would expand like cov alpha cov xy plus beta cov yz. And you can combine the two cases. But bilinearity means linear in each of the arguments. So the effect is, what would happen is that effectively computing, let's say, cov, let's say alpha x plus beta y and I don't know, gamma z plus delta w. If you want to compute something like that, effectively it would look like as if computing this is similar to expanding alpha x plus beta y times gamma z plus delta w. So think of just multiplying things out. What would happen if I just multiply these two? P has something here.
Gamma.
Sorry?
Alpha x times gamma g.
Right.
Yeah.
So I'm going to pull this, so say alpha gamma xz plus alpha delta xw plus beta gamma yz, right, plus beta delta yw, right? Is that right?
Yeah. Yes.
Yeah. So if you understand this, then the covariance, this is exactly bilinearity. So this operation is bilinear.
Oh.
So that covariance would be alpha gamma, you just replace this with covariance of xz plus alpha delta, the same thing, just this would be the covariance of xw plus beta gamma covariance of yz plus beta delta covariance of yw. Okay, so you don't need to remember or like memorize anything, as long as you understand how to like expand the product of two sums. The same rules apply, right? So if I want to do this, it's like, how do I expand something like this? If you expand it, you get x1 squared plus 2x1 x2 plus x2 squared. So here, if you want to really expand it without symmetry, what would you get? You'd get x1 x1 plus x1 x2 plus x2 x1 plus x2 x2. Okay, and then you use the symmetry to combine the two. You get 2x1 x2, and then you call this x1 squared because that's how what it means. So the exact thing happens for the covariance, because covariance is also symmetric. Exactly this would happen. So you get the this would translate to the variance. It's like covariance of x1 and x1, and then to the covariance of x1 x2 plus variance of x2. Okay. So that's how it goes. Is it clear to people?
So the final result is 1 plus 2 row plus 1, or
so you're looking at a different example. We don't have any row. So if you're looking here
yeah,
at this example, this would be just
example,
1 plus 1. Right? Yeah, so how about, let's say now, if you understand this, what would be the variance of x1 minus 2x2? How do we get this?
The covariance x minus x1 minus.
Right, we could do it, but let's say the thing I mentioned, so this is like expanding this.
Yeah.
Like this. So can you expand it?
Yeah, the variance x1
Right.
minus 4 covariance x1 x2
Okay.
plus 4 the variance x2.
Okay. That's correct. So everyone sees how this is done.
Yeah.
And then if you, okay, good. If you like, you could do this. Right, then you just have to do something like this in your head. Right, and you can see how this goes. Like the variance of individual times twice the covariances and plus something, right? So just have to be able to expand this. Right. Everyone happy with the situation? Actually, there's no something, so it's like can be variances of x1 plus variance of x2 plus variance of x3 plus twice the covariance of x1, x2 to covariance of x1, x3 plus 2 covariance of x2, x3, all the pairwise. And then you can verify that this is actually true by doing this operation on the general covariance matrix. All of this you can also prove using the other technique that we have. Okay, so these are two common approaches. Any questions? All good. So we did, again, a lot of examples because this is quite important, and I want you guys to get comfortable computing covariance matrices and variances, covariances, cross-covariances, any linear combinations of any number of variables. So these ideas are related. And so you should be able to now do these using at least two different approaches, and you can go through this exercise. This is another example that we did in pre-recorded lectures, and you can do it yourself. So how about this? Has anyone looked at this one, this result?
Yeah, yes.
Okay, good. So what is it saying?
The covariance matrix is always positive semi.
Okay, yes. So what is positive semi-definite?
According to the previous lecture, it's always greater than equal to 0.
So if you form these quadratic forms, this is a quadratic form. For any a, this would be non-negative. That's the meaning of the matrix. So matrix A would be positive semi-definite if, well, let's say matrix, I don't know, B would be positive semi-definite if A transpose B, A would be non-negative. And we just showed that this quantity, A transpose, remember, A transpose covariance of XA, this is just the variance of this linear combination. So in order to show that this is non-negative, we can show that this is equal to the variance of A transpose Y. We can show that this is non-negative, and this is always non-negative. Why is it always non-negative?
Is it 1-by-1 matrix?
It's a 1-by-1 matrix, but why is it non-negative?
Variance can never be negative.
Great. Variance is always non-negative, or another way of saying it is never negative. And so it just follows from the negativity of the variance. So combining lemma 3 with the fact that the variance of any random variable, so this is a random variable. It's a linear combinations of random variables, so it's a random variable, has a variance, and the variance is always non-negative, and the variance turns out to be this quantity. And so if you go back to the definition of positive semi-definiteness, this is exactly what it means for the covariance matrix to be positive semi-definite. So it's like a one-line proof, but combining two. This is by lemma 3. And the fact that the variance from the definition is always non-negative. So one of the consequences of this is that I know something about the eigenvalues of the covariance matrix. So what are the eigenvalues of a covariance matrix? Or what do we know about them?
They're always greater than or equal to 0.
Yes, great. That's another characterization of PSD-ness. So the eigenvalues are always greater than or equal to 0, i.e. non-negative. So what else can we say? And this is, so this is, in fact, if and only if. So what it means, what I mean is that a covariance matrix, or a matrix is a valid covariance matrix if and only if it is positive semi-definite. So we have shown one direction, that if a matrix is a covariance matrix, it should be positive semi-definite. The other way is also true. If a matrix is positive semi-definite, then you can construct a random variable. There exists at least one random variable whose covariance matrix is that matrix. So this is a characterization, like a complete characterization. So for example, when I came up with this matrix, and I said, assume that it is a valid covariance matrix, what you need to verify is that whether this is positive semi-definite or not. If it's a positive semi-definite matrix, then it's a valid covariance matrix. It can be the covariance matrix of a random variable. Otherwise, this can't be a covariance matrix. So one way to do it is to compute the eigenvalues and then show that it's all the eigenvalues are non-negative. And there are other tests for being positive semi-definite. The definition is usually difficult to handle because you have to verify it for all possible vectors. The other criteria is, anyone? I mentioned this in one of the lectures, probably not the 2020 lectures, but the last quarter. So anyone else knows another criteria for positive semi-definiteness? Okay, maybe not. This is mentioned, I think, in the previous quarter. So the other criteria is that the determinants of principal submatrices all have to be non-negative. So principal submatrices are matrices that are submatrices that are constructed on the same indices for columns and rows. So if I take 1 and 2 and 1 and 2 here, this is a principal submatrix. This is not a principal submatrix because the indices of rows and columns are different. This is a principal submatrix. This one is also a principal submatrix. And the entire matrix is a principal submatrix. And these are individual coordinates or principal submatrices. So there are 6 principal submatrices, which is 7. This, and this, and then the whole matrix. These 7 matrices, if the determinant of all of them are non-negative, then the matrix is positive semi-definite. So this is why the determinant. It might be easier. So here you can immediately see, for example, the diagonal elements are all non-negative, so that rules out 3 of the conditions. The determinant of this is easy, determinant of this is easy, determinant of the other one is easy. So it's like 1/2 minus 1/4 squared. So those are non-negative. You just have to verify the determinant that the whole thing is non-negative. Then it would be PSD.
So, Professor.
Yeah.
So n by n matrix and all entries are positive is going to be the positive semi-definite matrix.
No, that's not true. So it doesn't have anything to do with positivity of all the entries. So we could have a matrix whose entries are all positive. It wouldn't be positive semi-definite. And we could have matrices that have negative entries and they would be positive semi-definite.
The converse is not true. Okay.
The converse, nothing is like, none of it is true. So being positive semi-definite only gives you that the diagonals are positive. Doesn't tell you about the off-diagonal elements. And this is not enough. So this is necessary, but not sufficient. And the way to see that the diagonals have to be positive, you can just take A transpose to be, let's say 1, 0, 0. Okay, then A transpose, let's say Cov X A, this has to be non-negative, and this would just pick the first element. So this would be the variance of X1. It has to be non-negative. For any matrix, basically, if you apply it to, let's say, matrix A, that would give you A1, 1. And if you apply it with, let's say, this would give you A2, 2. Because all of them have to be non-negative, then you can come up with vectors that sort of select those diagonal entries, and so all of them would be non-negative. But this is not enough. That's where that criteria comes in. But okay, so that's something not exactly relevant to statistics, but Todd just mentioned this. Questions? There is a little bit of discussion of what happens or when, let's say, the covariance matrix is strictly positive definite. Let's say eigenvalues are strictly bigger than 0. The case where in usual case, usually we assume that the covariance matrix is actually positive definite. The cases where it's positive semi-definite but not positive definite correspond to cases where there exists a vector non-zero such that this is 0. And these are pathological cases. So I'll talk a little bit about this in one of the lectures, probably 2020. I'm not going to go over there, but if you're interested, if a matrix has, if a covariance matrix is positive semi-definite, but not positive definite, it means that it has a 0 eigenvalue. Alternatively, it means that there is a vector A non-zero such that this holds, which means that the variance of that A transpose Y is 0, which then means that A transpose Y is constant with probability 1. So what it means is that in that case, there is a linear combinations of the elements of Y such that that new random variable is constant almost surely, which is a pathological case. So yeah, so we're gonna move on from that. So the last topic in this, let's say, chapter or this section of the discussion is decorrelation or whitening. So any one of you guys got the chance to look at decorrelation? Did you or did you not?
I couldn't.
Okay. So maybe for the next time, you can take a look at this. So the idea here is I have a matrix. I have a I have a random vector y, and I would like to find A such that AY, which we call Z, has covariance matrix identity. So can I find a transformation of Y such that the covariance matrix is the identity? And the answer is yes, you can do that. And for example, you can take A to be the inverse of the square root of sigma. So this sigma negative 1/2, you can think of it as you take the square root. If you remember, a positive semi-definite matrix has a matrix square root. And the square root is not taking the square root of every entry. Remember, there's a matrix square root, which you can compute via the spectral decomposition. So if you go back to these ideas, so we discuss here, there's a matrix square root, which has the property that A1/2 is A. And using the eigenvalue decomposition, you can compute this by just applying 1/2 to the diagonal matrix of the eigenvalues that appear in the spectral decomposition. Sigma negative 1/2 is just the inverse of that square root. So you can take the square root first and then take the inverse, or take the inverse and then take the square root. The inverse of a positive semi-definite matrix is still positive semi-definite. Another way of seeing this is that if A is U lambda U transpose, then sorry, if sigma is U lambda U transpose, the sigma 1/2 negative 1/2 is you can just apply negative 1/2 to the middle guy. So that's another way of doing it. So if the covariance matrix is positive definite, so if so assume that sigma is positive definite, which means we are not in this pathological case. So the matrix is invertible. Then I can form this matrix. And the idea then is that the solution of this problem is this matrix. So sigma minus 1/2 y would have covariance identity always. So that's how I can make a matrix whose covariance is identity. And covariance being identity is nice because it means that all the coordinates of the new vector are pairwise uncorrelated. So the variances are all 1, and there's no correlation between the entries. So that's why this is called decorrelation. Okay, why this is true, I encourage you to go through this. First, you can try to show yourself. This is an application of lemma 3 again. So this important lemma that we had. So you apply it with sigma minus 1/2, and then use the properties of the inverse and the square root to conclude that the result is the identity. So I'll say you should try this to show it yourself, and then if not, take a look at the proof and the discussion in the lecture videos. So the main idea is that you can find a vector. You can decorrelate a vector. So if you have a random vector who has a general covariance matrix, there is a linear transformation of it that makes the coordinates uncorrelated and the variance is all equal to 1. This is like the vector or matrix vector version of standardization. The way you divide by the standard deviation. So if you have a zero mean random variable, if you divide by the standard deviation, the variance would be 1. And you can think of this as multiplying by this is like dividing by 1 over root sigma, which is like the matrix version of the standard deviation. Sounds good?
Yes.
Yes, questions, comments? Okay, sounds good. So anyone got, so this is the end of that chapter. So there's one other preliminary chapter that discussion that we have to go through, and that's the multivariate normal distribution, the idea of multivariate normal distribution. So anyone got to visit this part? So anyone knows, let's say, even if you didn't get this far, knows what a multivariate normal distribution is? Have you seen it in previous courses?
Yes, I kind of remember
So what do you remember?
the formula.
For the bivariate the distribution, normal distribution, or like for the full multivariate?
Yeah, this one. Yeah.
Do you remember this formula?
Not 100%, but yes, I saw it.
Okay, so this slide is defining. So for the next time, I want you guys to go through the lecture video discussing the multivariate normal distribution. So this chapter sort of reintroduces or remind you about what it is, and then some of the properties. So the properties are more important than the formula in this page. But this is defining a multivariate normal distribution via its density function or probability density function. So this f that you see here, f of y, is a PDF, probability density function. So anyone remembers what a PDF is? So that's how one of the ways that you can specify a distribution. You can specify the probability density function. So what is a probability density function? Univariate case, anyone remembers? PDF, what does it mean? So let's say the univariate normal distribution for a univariate case, univariate normal distribution, the PDF is something like this: 1 over root 2 pi e to negative x squared divided by 2. So what does this mean?
It follows the normal distribution.
So a random variable follows a normal distribution if it has the PDF given here. But what does this PDF mean? What can you do with this?
Find the probability.
Find the probability. Okay, so how do you find the probability using this?
Take the integral.
So
given the interval, and then when you try to take the integral of it, then that's the probability of it, of the.
Okay, great. So that's the meaning of the PDF. So the PDF is a density. Density means if you take the integral over a set, that gives you the probability. So so if I take the integral, so you can draw the function, it would look like this. And if I am given an interval a to b, I'm going to take the integral, which is basically the area under this curve. And that area gives me the probability of lying in that interval. So basically f of x times dx gives you what is the probability that I'm like in a tiniest interval near x, and then you add them up over a to b. And more generally, you can take the integral over any reasonable set, any set for which the integral exists. So I can do it, for example, over a disjoint set interval. I mean, union of these two intervals. I can take the integral over this set, and it would give me the probability that I'm in the union of these two. I'm somewhere here or here. And so that's the idea. And this has this can be generalized. So you can think of X as a vector, A as a set in Rn. And when you take the multidimensional integral over that set, over any set of this function, it gives you the probability that the random vector is inside that set. So that's the meaning of the general meaning of the PDF. So for the next time, please go over these the discussion of the multivariate normal distribution. So there are a couple of properties, and just quickly, you can review them quickly, and then we start talking about the linear model next. So go over the multivariate normal distribution at least for the next time from the video lectures. Okay, sounds good. Questions, comments? Okay, if not, I guess we'll stop here. Thank you, guys.